My name is Sarah Perkins-Kirkpatrick and I'm a Professor of Climate Science at the Australian National University in Canberra.
I'm Iain Strachan, a former journalist turned science communicator. We're members of the Australian Research Council Centre of Excellence for the Weather of the 21st Century.
And this is Totally Cooked, the climate and weather podcast.
You sure it is?
Did I get it wrong again?
The pause, it was like, and this is Totally Cooked?
Okay.
Where am I? What's going on?
Where am I? That is how I feel today, yes.
In this episode, we're packing a raincoat, grabbing our sunscreen, and heading outside to learn what climate change is doing to our weather.
So first of all, a disclaimer. If you're following this series in order, we said last time that we'd be talking about the history of climate science and who made some of the most important discoveries. Instead, we thought it would be important to first talk about the relationship between climate change and our weather. This is what 21st Century Weather, the research organisation that we work for, is doing. And we might get in trouble with our colleagues if we only talk about the planetary scale climate change and not about the weather that we experience every day. Hopefully it might make it feel more real and relevant for you at home too.
Cool. Okay. So, Sarah, climate change is impacting the weather all over the world. And we want to find out what that looks like and what those impacts are. And although we're looking at the whole planet, this is a podcast recorded in Australia. So
Correct.
I think we should start with a quintessentially Australian weather characteristic. And it's something that you know a lot about. Can you guess what it is?
C, extreme heat.
It is. I haven't written extreme heat here in my little prep notes, but I have written heat. So yes, we're on the money. And helpfully enough, for someone who is giving themselves a crash course in climate and weather science, CSIRO released their State of the Climate report recently.
They did, yes, a few weeks ago from when we were recording.
Anyone listening at home who doesn't know, because I didn't used to, CSIRO is the Commonwealth Science and Industry Research Organisation, who is a partner of our Centre of Excellence and obviously do a lot of very cool science and research, as the name suggests, Australia's National Science Agency.
To check, was it also in collaboration with the Bureau as well? That might be something that we need very clear on.
It was actually, that's right.
Yes, yeah.
Yep.
So the State of the Climate, it's a collaboration, a regular collaboration between CSIRO and the Australian Bureau of Meteorology. So yeah, they work together to produce this as a regular update as to how our climate's changing.
And they are both formal partners of this Centre of Excellence that we both work for.
They are. They're two of our research partners, and we tend to work, the community tends to work very closely together anyway.
Our friends at CSIRO and the Bureau have given us some very cheerful information as a jumping off point. For this
Isn't
episode.
it just joyful what's happening here?
Well,
I say that with the utmost sarcasm.
I picked out a few little bits that I might read out. I don't know how much of this, we will go into, but they said that Australia on average has warmed by 1.51 degrees, give or take, plus or minus 0.23 degrees Celsius.
Let's just call it 1.51, I think.
On average has warmed by 1.51 degrees since national records began in 1910. And every decade since 1950 has been warmer than the preceding decades.
Yep.
Australia's warmest year on record was 2019, but 8 of the 9 warmest years on record have occurred since 2013, which is in the last 11 years. The long-term warming trend means that most years are now warmer than almost any that we observed during the 20th century.
That really frightens me, that one.
That's interesting, isn't it?
Everything else that you've read out is not a surprise to me. Don't get me wrong, it's still really concerning and, frightening. It's matching most of what's been happening globally, but that last one, that pretty much every year that we have now is warmer than years, even 25 years ago or longer.
What might have been, if it was, say, 1997, I don't know if that was a hot year or not off the top of my head, but let's say you had
There was an El Nino that year, but yes.
Let's say you had a stinking hot year in the late 90s and you'd be like, oh my God, I've never known anything like this. That's every year now.
I think the thing that frightens me the most, my children who are 7 years and under have not experienced and will never experience something that's reasonably close to average, being all born well after 2000. And that wouldn't obviously just affect my children, but many young people out there, and basically anyone over the age of 22, 23. Yeah, that's a really hard pill to swallow.
This is bad, or it's certainly very troubling.
Yeah, we're not
isn't
starting
it?
off on the most joyous of notes, are we?
Yeah, I know. I thought, oh, cheerfully, well, let's go outside and look at the weather. Like, weather's more interesting, climate's scary, weather's fun, but it's like you can't really separate the two, can we?
No, well, and especially with something like extreme heat or heat waves or however you want to call them, they are very closely linked. But I guess we'll get into that a bit more as we go on.
Well, that's exactly what I want to talk to you about. So the last thing I wanted to quote from our friends at Cyro was that in their report, they said there are an increased number of extreme heat events across all months, including a greater frequency of very hot days in summer.
Yep.
You study heat waves for a living and you're very good at it.
I do. Thank you.
Yeah.
I'll take that as a compliment, I think.
I mean, that's what that's what I've been told, you know? And
Okay. Yeah.
and I would like you to tell us, Zach and I and our dear listeners, what an extreme heat event is, please.
Here in Australia, we do have like a formal heatwave definition that the Bureau of Meteorology has produced. And it's when we have basically at least 3 days in a row, maybe more, but it has to be at least 3 days in a row when temperatures are above the 95th percentile for that location. And basically what that means are that in the top 5% of days, so they're those really hot extreme days, when that occurs, those days have to line up in a 3-day window or longer.
What's the longest heat wave that you're aware of in Australia?
The heat waves in Australia actually don't last for that long, not like some places overseas where they've literally lasted for over a month. Here we actually had a really bad one. Some listeners might remember in 2009 in Southeast Australia. That really hit Victoria hard, but the heat wave itself did push up into New South Wales as well. But it was an on again, off again type heat wave. So it was really hot for a while. Then there was a bit of a reprieve. And then, this real sting of heat came towards the end, which then contributed to some really bad bushfires. But usually because of just how quick the weather systems move that cause heat waves in Australia, it's rare to get one that lasts a week or more. But it's not unprecedented, but it doesn't happen very often.
So we talked in the last episode about the greenhouse effect and how increased levels of carbon dioxide and methane in the atmosphere is making the planet hotter. Is that why we're experiencing more extreme heat more often?
Yes, pretty much. So heat waves, as I mentioned, they're a rare extreme event. They're hot extremes, really hot. We don't like them. People die. There are lots of natural factors that contribute to heat waves. So I did mention there's an important weather system, which is either known as a persistent or a blocking high. There are interactions with the land surface. So if it's really dry and we're in a drought, that increases how intense heat waves can be. The interactions with urban areas, because urban areas trap more heat in, particularly at night, that can increase the temperature. So all these factors contribute and or drive heat waves. But the main thing or the main issue that's driving an upward trend in heat waves is human-induced climate change. More carbon dioxide is keeping the planet warmer for longer. That's making global average temperatures increase. And if the average temperature increases, so do heat waves. And we're seeing more of them. And when they occur, they're worse. And I guess something that's really important to remember that, we're only seeing technically average temperature increase by like a degree, but we're seeing some heat waves now occur that are multiple degrees warmer than what they otherwise would have been. And that's really troubling because, yes, that relationship is very clear, but it's very sensitive. So it's just a small shift in average conditions can mean really big, bad changes when we're talking about heat extremes.
And of course, we said that Australia's warmed by 1.51 degrees, but we're likely to get up to 2 and beyond, right?
Well, yeah, this is the really unfortunate thing, right? So Australia's a landmass. Land warms faster than ocean. We are warming a little bit faster than the global average, although this year, 2024, is meant to be the hottest year on record, where we will scrape 1.5 degrees Celsius. So if you think about how warm the globe has been this year, Australia has been just a little bit warmer than that on average. As you said, I do study heat waves. They're kind of like my, pet, if you will. I won't say baby. My other babies might get upset with that. But yeah, it's not an easy thing to study all the time because of just how quickly those changes are happening and the impacts that those changes have. And,
we hope that we obviously have an Australian focus, but we hope that we'll have international listeners. Heat waves, not just an Australian problem.
No. And this comes down, as I mentioned, it's just got to be really hot for a number of days in a row. They must be relative to the location. So that's why I talked about the percentiles or being in the top 5% of days. That's always relative to that climate. So you can get a heat wave in Antarctica, technically speaking, as long as you're basing it on that climate. Like you can get a heat wave where I am in Canberra versus, Chicago, London, because it's all based on the climate conditions there.
I mean, speaking from personal experience, a heat wave in Scotland is lovely.
It'd be freezing to me.
I mean, I don't have the data at hand, so we should check it before we go on about it. But like, I'm imagining a heat wave in Scotland is like 27, you know?
I reckon it'd actually be a little bit less than that. It's funny, it's funny being in London, and it's happened to me, like, beautiful 28-degree day. And I'm like, that's my optimum temperature, by the way, is 28 degrees Celsius. Love it. And we're as the Australians walking around just enjoying, and you can see all the Brits like sweating buckets and complaining that it's too hot. I'm like, what's wrong with you?
London doesn't cope well with the heat because it's like, it's not built for it. The tube isn't air conditioned.
Tube, yeah. No, the tube was another 20 degrees hotter than that, and I did almost faint when we went on the tube. But notwithstanding, outside was just delightful, and just to hear everyone whinge, I'm like, oh, you guys don't know.
We've gone on like a cheerful little, Brits struggle in the heat digression, but like the thing that I want to talk about now from Sarah is this is very worrying. It says, Sarah says that extreme heat has caused more deaths in Australia than any other natural hazard. Is that correct?
The first time I heard that statistic, my eyes were wide and I was like, oh my God, that's a lot. But when you think about it, like, it makes sense. It's, we love the sunshine. We love to be out in it lots. We do get other climate and weather related hazards like tropical cyclones and floods and droughts and all that sort of thing. But heat is, definitely our largest killer by far. And, the heat wave that we had in 2009 over southeast Victoria, the excess deaths that occurred in just 1 week was 374. But extreme heat would be the one that's the biggest killer there.
Flooding and fires, are very dramatic and
yes,
very visual, very immediate. They're in the news. They're, the emotive stories come out of them, and there's something that grabs our attention, both personally and in the media and in social and cultural discourse. But it's heat, extreme heat, that kills more people, but it kills them quietly and less sensationally and less tangibly. And so from your perspective as a scientist working in this area, like, do you think we take the risks and the threats of extreme heat waves and the likelihood that they will increase, are we taking that seriously enough? Do we talk about it enough? What's your view on that?
So personally, I don't think we do, particularly coming from a country where, I just use the example, like 28 degrees is my optimum temperature, whereas you'd probably keel over and lie down at that.
I'm going to the beach. I'm taking the afternoon off and going to the beach today with a friend who's Australian but visiting from London.
Yeah, I don't think we do, because we're just, it's inbuilt to our culture that it's hot. We love it here. But on top of that, like, there was a report that came out a decade ago saying that heat waves are the silent killer. And that's true, because it isn't that dramatic death. I hate talking about mortality and death, so I do apologise to the listeners if I'm throwing these terms around willy-nilly, that I'm not. It's just, unfortunately how we need to talk about these events sometimes. But it's not instantaneous. It takes time for the body to react to those conditions. And also at the same time, you can drown very quickly within a few minutes of being submerged. But with extreme heat, you need to be exposed for at least a few hours or so to have that irreversible effect on your body. So it doesn't necessarily happen straight away. And oftentimes when the deaths do occur, it's 1 to 2 days, maybe a bit shorter, but up to 1 to 2 days after the extreme heat has occurred. So it's not something that just happens and we can measure straight away. It takes time.
This is how the media works. This is how government and policymakers work. If you're giving evidence and inquiry, like, your area of expertise is the kind of the climate and weather processes around heat waves. But my instinct is to be like, what do we do? We know it's going to get hotter. We know we're going to have more heat waves. How do we respond? What should we do? Gosh,
this is something that internally I struggle with a lot. But what's something that we're working on now is, what happens when we reach net zero? Once we finally don't have all this extra carbon going into the atmosphere, what happens with extreme heat then? And the initial results I'm looking at is nothing gets better. Where we finish, or where we start net zero from, where we finish, putting more carbon in the atmosphere, heat waves stay at, and in some locations they still continue to increase for guess what, at 1,000 years. And that's what concerns me the most, is we have known about this, interaction with carbon going up. Heat waves will go up because global temperature goes up. But once we stop emitting that carbon, because there's still so much carbon dioxide sitting in the atmosphere for what turns out to be a very long time, nothing actually will get better. It may prevent it from getting worse, but it won't get better. And that therefore means we must adapt and we must mitigate. We've passed the point where we should only rely on reducing our greenhouse gas emissions. That ship sailed long ago. We have to adapt. We've got to mitigate against these events when they occur.
And it's something that I think will come up in this series a lot, and even that we'll have a particular episode about later, which is the kind of concept of climate justice and the things you're talking about there, like access, not being able to afford to cool your home, not having air conditioning if you're living in rented. Not
even air conditioning. See, this is the thing, and I've noticed this very much anecdotally in my own experiences. Everyone reaches for the air conditioning remote. Sorry, I shouldn't say everyone, because I know some people can't afford to run it. I get that. But the humble fan can do a lot. In fact, up to like 37, 38 degrees, it's really effective in people keeping cool. Yes, you won't be hit with this wave of 20-degree temperature from some box in your wall, but it will keep you cool enough for you to function normally. For people who can't afford air conditioning, it doesn't mean that you can't keep cool. There are other ways to do that as well. So I think, and air conditioning is part of the problem, right? Because they pump so much greenhouse gases into the atmosphere. There are other ways that we should be looking at instead of just saying to everyone, well, turn on your air conditioning, because that also drains power supply during a heat wave because everyone wants their air conditioning on to 20, 18 degrees. We also don't need that. Put it on to 26 or 27 degrees. Not only do you save power, but you're able to, cope with relatively warm conditions and not freeze.
And building quality and energy efficiency in housing is a huge issue in hot countries. A hot country like Australia, like our houses are not built to withstand the heat. We think they are, but they're actually very poorly built.
How long do we have today to record this podcast? I could talk about extreme heat for many, many, many hours. But there's a lot of issues with how Australians design their houses, both for summer and winter. Glorified tents has been thrown around many times in terms of Australian housing. And this is particularly a problem in Western Sydney, other areas too, but certainly Western Sydney, where it's already hot because of the local geography. It's 50 kilometres from the coast and at the base of a relatively modest mountain range, but one all the same. And the heat just sticks there during heat waves. You can have, Penrith, which is 50 kilometres from the centre of Sydney, be, in the mid-40s, and Sydney City itself being in the low 30s, just because of the local geography alone. But then we have a high population boom out there. Everyone's living in these great big houses that are really close together with no natural vegetation and black roofs. And that is a recipe for disaster. We haven't had any major heat waves in Australia in recent years, and there's reasons for that. But when we do get our next one, that's a real problem because a lot of those houses are fit with air conditioning. They will drain the system because they just want to stay cool. Who can blame them? Because they're trapping all the heat into that local environment. I'm really frightened to think about what happens when we do get that 50-degree heat wave in that part of Sydney. I think it would be catastrophic.
From our friends at CSIRO, they said in their State of the Climate report for this year that Southern Australia receives much of its rainfall during the cooler months of the year from low-pressure systems and cold fronts to the south of the subtropical high-pressure ridge.
What a mouthful. Subtropical high-pressure ridge. Doesn't roll off the tongue, does it?
Doesn't roll off the tongue, and before starting this job in this Centre of Excellence, reading about the weather and the climate, I didn't understand a lot about that. And still am learning about it. And I think that, we're so used to seeing, older people like us are so used to seeing the weather on the TV.
I'm sorry. What did you just say?
Older people. So what I'm saying is, right, so actually, here's another.
No.
So my question for you, Sarah, is what is a low pressure system? So
if you happen to have a TV and flick on the news, or even it's not even necessarily on TV, you can get weather maps anywhere these days. But you see lots of squiggly lines and a few letters. A low pressure system is represented by literally an L with some circles around it. And that just basically tells us that at the bottom level of the atmosphere, which is where we live, we call it the surface or mean sea level pressure, but at sea level, the pressure there, the atmospheric pressure, is lower than normal. And if it's got circles around it, it means that it's its own system. It's not getting any sort of air moving into it or very little air moving into it from, directional wind flow. So, I was going to use the term jet stream, but that may be a bit much for...
Well, it's good. I mean, it's good to talk it out on the air and work out how to explain it in ways that we all understand. Check my understanding, right? A low pressure system is a sort of a little bit of weather where because the pressure is lower than the air pressure around it, it's kind of on its own.
A little bit, yeah. So sometimes you can have what we call a cut-off low, and this is what things like hurricanes and tropical cyclones and typhoons are. And even in Australia, we get a system called an east coast low, and they're what we call cut-off low. So they are cut off from the directional flow. So they may not move the normal way the wind moves. They're their own little system. They don't last forever, thank God. But yeah, that's generally when we get the more extreme rainfall. Yeah, but if it's if you see an L on a map or just want to know what a low pressure system is, it's that sort of area in the atmosphere where the pressure is just lower than normal.
Okay.
We have pressure above us. We measure it in hectopascals. This is just fun facts or, tidbits, but usually it's around 1,000 hectopascals.
Is hectopascal Pedro Pascal's brother?
I don't know who that is.
Oh
wow, both of you are freaking out. Holy shit, I'm showing my age, aren't I? Maybe a maze will be 100 if I don't know who. Let me Google him. Who is he?
You must. Pedro Pascal. This is extraordinary. I feel like...
I don't like big noses. He's got a big nose.
Sarah, I feel like in this moment you are 3 years and 3 decades older than me.
Oh, that hurts. What's he in?
Game of Thrones.
Is he...
The Last of Us.
Oh, was he in some sort of like cocaine movie?
Narcos.
Narcos, that's it.
Like so
famous. There it is. Yeah. We tapped out of Game of Thrones. It got too much. And I don't have a life.
It sounds like when it comes to popular culture, you might be in a cut-off low.
Yeah, I'm in my own little system, my own little ecosystem. Yeah, it's just his nose. I can't get past his nose.
He's also, like, if you've seen him in interviews, like he's very meme-ified because he's so charming and like...
all right, that's my homework, is to try and find time to watch something other than Narcos. Anyway, all right. Yes, we're still here. Oh, we've talked about low pressure.
To calm down from getting excited about Pedro Pascal, we might need a cold front now.
Okay.
Can you tell us and our dear listeners what a cold front is?
The hint's in the name with that one. It's a band of cold air that kind of sweeps through. It undercuts some warm air when it happens, and it can sometimes bring rainfall, doesn't always. But as the warm air that it undercuts moves up into the atmosphere, that then can form rainfall, and then it comes out of the sky. So oftentimes they're on like the eastern flank of a cold pressure system. Again, not always. It just depends.
That's in Australia.
Yeah, in Australia. You can get cold fronts anywhere. That's just, but they move around. They don't last forever. I mentioned earlier in this episode that heat waves, they're caused by a persistent high pressure system. That's effectively the opposite of a low. And in general terms, high, you think of it's stagnant air. It's not windy. We bake. It's hot in summer anyway. It's just calm weather with lots of clear skies. Generally speaking, the low pressure systems are the opposite of that. And they're associated more so with rainfall. And a cold front is oftentimes what sits in between the two. So as the low pressure starts to move across and we get a change of weather, it often starts with that cold front coming through first. So
is it too simplistic to say that the weather is just wind and air pressure doing stuff?
And moisture.
Yeah.
And it moves around, warmer air holds more moisture. If that air gets cooler, that moisture comes out and we have rain.
And so when you get a cold front coming through, you get changes in temperature, changes in wind speed and direction, and sometimes you get rainfall.
That's right. Well, hot air rises, right? So if you have a cold front come through, it undercuts that warm air rises, gets colder as it moves further up in the atmosphere because that's just what happens. All that moisture comes out, rain.
And hot air rises because heat rises? Like, why does
I was going to try and make a joke. I was saying no, just because we all fart a lot, but that's probably not PC.
Why does hot air rise?
It's more buoyant.
And that's the same with water, right? Like in the ocean.
Yeah, correct. They're both fluids. So
fluid dynamics.
I won't go into that. I don't know a lot about fluid dynamics, but they're both effectively fluids. It's just the scales on which they operate are different, but the same principles apply. Dense, heavy stuff sinks. Hot, floaty stuff rises.
That's the level we'll look at. We're getting dangerously science.
You're getting that, yeah. I know. I was like, well, it's just a cold front. It's just cold and it's
just cold.
Air.
Yeah, so cold fronts come in, particularly in Australia. you might get a large difference in air temperature, and cold
Yeah.
fronts can kind of be, am I right in saying they can be like a line of cold fronts that can be,
Yeah, pretty
or
much.
a cold front can
It's-
be a line of, hundreds or even 1,000 kilometers long.
Absolutely. Yeah, yeah. And that's what happens. Like, particularly during winter, we can get cold fronts any time of the year, but you can see them, they come up from the Southern Ocean. You can see it come, again, I'm thinking about a weather map because I love them. But if you do happen to look at one, you can see like this big line and it'll have triangles on it. And those triangles symbolize a cold front. But it's not just like a little bit here and a little bit there. It's on the flank or the edge of that cold air mass moving forward. And it's a big long line. It just shoots through.
And this might be a really naive question, but because it's coming from the Southern Ocean, that's why it's colder, because it's at the poles? Like the weather's been hanging around at the poles and it's colder down there at the poles?
Sometimes it can be. Sometimes you can get bursts of cold air that comes straight from the polar region, so comes straight from Antarctica. Sometimes, not always the case. It's just that in this case, it just happens to be the location because, you have the air masses, as I mentioned, you might have like a cold air mass. So you might have a warm air mass and right behind it is a cold air mass. And it's that sort of, the boundary between the two, that's where the cold front tends to sit. But it's not typically that much colder because it's always coming from a polar region. But you can, and we have had them, we had them this winter actually, where we did get like large bursts of specifically cold air from Antarctica. Like it's almost like the gates opened up and we get all this cold air.
So the last time I was living in the UK was 2015 to 2018, and there was a year, I think 2 years in a row, 2017 and 18, there were multiple major like cold fronts or like polar vortexes coming in from the Siberia and the Arctic.
That's the term.
Yep.
That's the term I forgot, polar vortex, and how that operates.
They called it the beast from the east. And it created a lot of chaotic like snow and ice.
Yeah, and that happen in Northern America as well. We don't get them to the same strength because we're not
because we're further
as far
away
south
from the pole.
Yeah. But we do, they do have like they're much rarer in Australia just because of the dynamics that happen, and I won't go into that. But we do, yeah. It is literally like the gates just open and the air mass just escapes. The cold air mass escapes.
It's a fun image.
We freeze.
Well, thinking about the difference between winter and summer, the last part, and we've taken quite a while to unpack that juicy sentence from Cyro. The last bit is the subtropical high pressure ridge. Can you have a go at explaining that to us, please?
It's a ridge of high pressure that sits in the subtropics. Does that work? Will everyone understand that?
So I mean,
Zach, you're not nodding.
why don't we unpack it, right? So we've talked about high pressure. That's good weather.
High, well, let's not say good because it can also mean very, very, very hot. But yes, high pressure is calm weather.
Okay. Subtropical, like Australia is, covers both the tropics and the subtropics.
Temperate. Yeah. So we go from the tropics, like Darwin, for example, and Cairns, they all sit in the tropics. The Tropic of Capricorn, so that tells us, is it Capricorn in the Southern Hemisphere or is it Cancer? I'm pretty sure it's Capricorn. You should know this, right?
It goes through Rockhampton, doesn't it? Around there?
Yeah, it does. So 23.5 degrees south. That's where that line sits that differentiates between the tropics and the subtropics. So Brisbane is somewhat of a subtropical city. Then I'm moving further south. And Sydney is very much a temperate city. So is Canberra. Different levels of temperate because the local climates differ a little bit. And I would even say that Melbourne and Hobart are temperate climates as well. But yes, from way up north, that's where we're closer to the equator. It's different in the northern hemisphere. But then down south, so we do go across many different climate, specific climate zones.
But what's the deal with this ridge? What is a ridge?
Yeah, so this ridge, the ridge, it's just basically a band of high pressure system that sits in the atmosphere. That
kind of is there a lot of the time, right, in Australia?
Yeah, it's like, it can break. So you can have, little bits shoot through it. But it just, in summer, it moves further south. It tracks the sun. And, obviously in summer, regardless of where you are in the world, you receive more sunlight because you the planet flips towards the sun.
And so when it moves further north, in the Australian winter, the austral winter, then more cold fronts get through because it's not there to protect or buffer them or filter them. Is that right?
Yeah, it seems like the low pressure system or the rainfall systems underneath it, they tend to shift further north. Yeah.
Okay.
But what's actually happening and what this State of the Climate report reported was we're not seeing that happen so much anymore. So the southern tip of Western Australia and southern Eastern Australia, so Victoria particularly and Tasmania, they're not getting that wintertime rainfall. Those pressure systems, those weather systems that used to be really important for driving wintertime rainfall, they're decreasing, they're declining, and so with that is that rainfall amount.
Sarah, you have preempted my next question. That's very naughty.
I like this. I'm not even looking at the script. I'm looking at myself and my big bags under my eyes.
So, I mean, that's exactly right. So we've talked about the kind of the systems, the processes that where Australia, Southern Australia, like Southeastern, Southwestern Australia gets a lot of its rainfall from. And climate change is changing those processes.
Yes,
Yeah.
It's just a yes. Yep.
It's just a yes, yeah. So I might actually, zero in on what CSIRO said specifically about that. They said that there's been a shift towards drier conditions across the southwest and southeast, which is what you've just said. More frequent periods of below average rainfall, especially for the cool season months. Winter. Now, they said that this is due to a combination of natural variability on decadal timescales and changes in large-scale circulation driven largely by an increase in greenhouse gas emissions.
Yeah, so what we're seeing with climate change is, hopefully this is as sciencey as I get today. We have a system or a modulator, if you will, or a driver of Australia's weather and climate called the Southern Annular Mode, or the SAM, we call it for short. SAM's a little bit easier to remember, but yeah, so what it is how a band of pressure moves, or it circumnavigates the southern pole. And with the Southern Annular Mode, it means different things in different seasons of the year. And I always get it wrong. I always have to look it up precisely what it means for the season that we're in, because it does change. Sometimes in summer, depending on what phase of the SAM we're in, we might get more rainfall where we are, but other parts in Australia might get less rainfall. It usually only affects eastern and southern Australia. So it does flip depending on the season. But what's happening during winter is the Southern Annular Mode is shifting further south, and those rain-bearing systems for southern Australia are starting to decrease because that band is shifting further south. And this is it's surprisingly consistent, not just obviously in our observations, which is what this report is based on, but also in our climate model simulations. They all say this. And we could see this happening when I was doing my PhD 20 years ago. And that was with some really basic climate models. So it's a very consistent feature. And yeah, as the report says, there's a significant signal because of the fact that the planet's warming.
And we shouldn't forget, so we've talked about Southeast and Southwest Australia receiving less rainfall, but we should also remember Northern Australia, where it is in the tropical regions particularly. CSIRO said that Northern Australia has been wetter than average over the last 30 years across all seasons, and 7 of the 10 wettest Northern Australia wet seasons have occurred since 1998.
Really intriguing. So there's a few things that's going on here. Firstly, we've just had a few really wet summers. We've had triple dip La Niñas. Some of, I don't think we're going to unpack that today, but I'm sure we'll unpack what a La Niña is in other episodes. But that generally brings more rainfall to northern and eastern Australia. On top of that, a warmer atmosphere can hold more moisture. Specifically speaking, increasing the atmosphere by 1 degree Celsius means it can hold roughly 7% more moisture relative to the previous degree. And if we've warmed up, even 70% more moisture is actually a lot in absolute terms. So there's, the atmosphere in the tropics is just like pumped to rain. There's just so much more moisture there. So when you do get the triggering effect, more rain falls out. And we actually see that a lot with extreme rainfall in other locations as well. So it's just it's primed, it's ready to go. And if you have the monsoon come through, it'll fall out. There's other systems that make it come out more quickly during the monsoon season or the rainy season. There's likely a mixture of natural variability and human-induced climate change that's driving that rainfall response in the tropics at the moment.
It's just interesting that, I used that report as the basis of my research for structuring this episode with you, but you kind of thought a lot of it already, like you're kind of you're one question ahead of me in a really good way. Like the final thing I was going to quote to you was CSIRO said, many of these trends are consistent with simulations from climate models, which that increased greenhouse gases lead to fewer low pressure systems in southern Australia, stronger subtropical ridge, but an increase in the intensity of heavy rainfall, including from thunderstorms. And that's the point about there being more moisture to rain with.
Yeah, that's right. And we have actually seen in some regions that when we do get that extreme rainfall, and it is much harder to study extreme rainfall than seasonal rainfall, for example, but that sort of, degree increase, that relationship we expect to see with how much more it rains relative to the temperature is actually much higher than the average conditions. So there's actually likely more moisture there than that basic relationship originally tells us, which is why, we saw mass floodings in Spain recently. When we did have our triple dip La Niñas, they were really bloody bad because there was just that much more moisture there. And those sorts of, whether it was the weather event over Spain, that was a good example of a cutoff low, or, the longer scale modulators that drove the rainfall events and the flooding events we had in Eastern Australia over the last few years, they're the triggering mechanisms. They're there. They make the conditions, more laden and more prime for extreme rainfall, and the moisture's just sitting there ready to go.
So I'm really grateful that you touched on the southern annular mode, and you also mentioned El Nino there.
Our mate Sam.
Sam, g'day Sam. Those are such interesting topics that we want to get into them in more detail. Like, we're going to do whole episodes focused on those kind of major modes or kind of climate drivers. So we're going to go into them in more detail.
Yeah. That's what I thought.
But suitably, you've just brought up the idea of heavy rainfall, like flooding, the flooding in Spain that we saw, the flooding in Australia in 2022. So we've talked about rain a little bit. Let's talk now about what happens when we get too much rain. I'm doing air quotes here for anyone who can't see the video.
Yeah, too much rain is bad. Like, too much heat is bad.
Yeah.
Systems can't cope, especially in built-up environments. The water has nowhere to go, and bad things happen. Done. Next.
That's so easy. No,
Done.
So that's it. Yeah, quick heavy rain causes flash flooding in towns and cities. We've got lots of tarmac, lots of concrete, asphalt. We can't absorb it. We can't channel it, especially if we've had lots of extreme rainfall, or even just lots of rainfall in general in the lead up to that event, because soil is saturated and it can't absorb as quickly. But if you also take that soil away by building cities and other impervious land surfaces, the moisture, literally cannot go anywhere unless we funnel it down our gutters and waterways. And you've talked already a little bit about what kind of weather systems and processes lead to heavy, rain. And it's thunderstorms, it's tropical cyclones and monsoons, East Coast lows you mentioned. And you've also talked a little bit already about how climate change is affecting heavy rainfall. So you gave us that statistic of, was it 1 degree of warming equals 7% more moisture?
It's what we call, and you probably want to edit this out, but it's the Clausius-Clapeyron relationship. And don't make me spell that because I can't. But it was put together a long time ago, just based on physics really, that if you heat air up, the water vapor or moisture it can hold roughly increases by 7%.
Warmer air means more water vapor.
Exactly. Yep. Exactly.
So a warmer climate means heavier rain. Is it that simple?
Basically, yes.
And
next.
I mean, let's sound the attribution klaxon, which can be fraught, but how when it comes to heavy rainfall, like extreme rain events, let's focus on Australia for now. How specific can we be at the moment about blaming climate change or attributing climate change? And
this is a really good question, and I do need to be a bit careful here as well, because I don't want what I say to be misinterpreted. I'm not going to say that every extreme rainfall that we've ever had in recent years is due to climate change. It's not a categorical yes or no. Right? We can't do that. So let's just say that now and draw a line in between that, because I think that's really important for everyone to understand. What we can potentially do, and here I'm talking about more generally when we talk about weather extremes, is potentially work out whether or not climate change was a contributing factor. So was that typhoon more likely because of climate change? Was that heat wave more intense because of climate change? And we use a mixture of physical climate modelling and observations to make those assessments. But there's a lot of, I wouldn't say caveats, but there's a lot of things that we need to consider. That firstly, every single extreme event will have their own climate change signal behind it. So just because one heat wave was made 5 degrees hotter because of climate change doesn't mean that every heat wave was made 5 degrees hotter because of climate change. It's unique. It's bespoke to that event. Secondly, it does depend on the methods that we use. So different models may spit out slightly different amounts. I would actually argue, at least for extreme heat, that they'd all come back and say, climate change is making this event more frequent or more intense. But the precise amount will differ from the framework that we look at. And the same would be for any other type of extreme. So if we're talking about extreme rainfall, it is a bit more difficult to attribute specific events to climate change because of the scales that rainfall occurs on. It's harder for our climate models to simulate those processes accurately. But we can say, based on those physics that I was talking about, that Clausius-Clapeyron relationship, that 7% more moisture relative to temperature increase, that we're much more likely to see more extreme rainfall. We're much more likely to see higher amounts of rainfall occur when we have extreme rainfall events, because the atmosphere is just more laden with moisture.
And am I right in thinking that one of the difficulties we have with this in Australia in particular is that the differences in rainfall from year to year are higher compared to other places in the world? Like we have big variances around here.
Our climate is very variable because we have all of these different climate modulators or drivers. So I mentioned our mate Sam. There's also the El Nino Southern Oscillation effect. There's a Madden-Julian oscillation. There's the Indian Ocean dipole. I'm not, no one needs to understand what they mean really now, but it's just a hint of, the sorts of mechanisms that affect us. There's multiple. It's not just one or two. It's much harder to predict Australia's seasonal changes, and not so much day-to-day weather, but certainly what will happen from one season to a next, because it just depends what modulator is active and what's not, and also, obviously the background role of climate change.
And so I think, to try and sum up a little bit about what we've been talking about when we've moved from rain to heavy rain, is that as you've said, our climate model simulations tell us that heavy rainfall will increase this century proportional to global warming.
So we will see an increase because of global warming. Just how much rainfall falls during an extreme rainfall event, how much time can I say fall in a sentence? It does depend. There's a lot of variability around that, but it definitely will rain more when we have these events.
And then in terms of the uncertainty that we're facing, there are all kinds of factors at play here. But to kind of try and capture it in one go, a warmer climate is changing our typical weather systems, and the impacts of that differ at global, national and regional scales.
This is where it all gets a bit juicy. It's hard to say whether specific weather systems will change. We don't actually really have strong evidence, at least for the Australian region anyway, that climate change is augmenting what causes heat waves, for example, so those high pressure systems. There's some evidence, actually increasing evidence now, that when tropical cyclones occur, that they will be more intense because the warmers that they draw their energy from is warmer, the atmosphere is warmer, etc. But we're going to see fewer of them. When it comes to rainfall events, it does depend what's actually driving that rainfall event. Is it a storm or just a really deep low pressure system? So sorry, that maybe was a bit too sciencey, but it's hard to say categorically that climate change is influencing all of the weather systems that we see.
Okay, maybe to conclude this little chat, I'd like to introduce a concept to our audience that we're talking about within the centre, within the researchers here. But that isn't being widely discussed yet, and it's the term weather change. So
yes.
So we've been talking about global warming and climate change for quite a long time now. At least since you and I were at school, like the 90s. And in the next episode, we're going to get into a really fun, like another trip in the time machine to the people who
in our fridge
going to get in the time fridge.
What are we going to take this time?
We're going to get in the time fridge and learn about who discovered climate change was a thing. But in our lifetime, global warming and climate change was always something that seemed like it was going to happen. Like this is something to be worried about in the future. And maybe that's partly to avoid worrying about it, like to kind of kick the can down the road and be like, oh, this is a tomorrow problem.
Well,
but
therein lies the problem, right? We couldn't kick this can down the road. It just doesn't work.
But it might also be because climate is the average of our weather. It refers to long time scales, the shortest kind of time scale, months, but, hundreds of years, thousands of years is climate. And weather is what we get day to day. And
climate is what you expect, weather is what you get, as the old saying goes.
Allegedly, that's attributed to Mark Twain, but no one can confirm that he said it or not.
I didn't even know it was attributed to anyone. I thought it was just one of those old things.
I think it might just be an old saying.
Centuries.
It might just be an old saying that someone wants to attribute to somebody famous, but yeah, climate is what you expect, weather is what you get. And
correct, yes.
And
so they are related, they're just not the same thing.
Not quite the same thing. Weather is today and climate is 10 years,
20, but yes.
20.
Or 30.
Or 30 or 1,000. What we've talked about in this episode, or what I'd like to think we've talked about, and we'll have to listen back to it and make sure we didn't stuff it up, is that the weather that we've been used to in recent centuries in our records and in our own lifetimes is changing.
That's correct. So the weather is changing. Sometimes we cannot say for sure if the systems are changing, but the weather is changing. Even just from warming the climate 1.5 degrees, even if we just see the exact same weather systems, how they influence our rainfall, our temperature, our wind, that is changing. We just can't tell for sure if all of these systems in how they work specifically is changing. But yes, our weather is changing because of climate change.
So the system's mechanisms might remain the same, but the inputs into them are different because it's hotter.
It's hotter and things are different in a warmer world. Even if all we do is just warm and then slap on the same heat wave or the same tropical cyclone, their impacts, it's not even really an impact, but how they, evolve and rain and not rain or blow wind or give hail or whatever, that will change simply because the climate's just that bit warmer.
And I'm going to put you on the spot here, and it might be a question that we'd rather give to the super boss, our director, Christian, but...
The Wizard.
The Wizard.
The Wizard of Oz.
The Wizard of Oz. Why are you and the researchers at 21st Century Weather starting to use this term weather change? Why do you think it's valuable and a useful concept?
Well, I think, at least from my perspective, and Christian, aka Wizard, might have a slightly different take on this. But, like you said, Ian, we've been talking about climate change for decades, literally. Longer, I would say, I would definitely say longer than we have been alive for. We've known about how human activity can change the climate. And we know broadly what will happen. It's going to get hotter. We're going to see more heat waves. Cyclones and typhoons will be more intense. There's all these things that we know that, yes, warming the climate or putting more carbon in the atmosphere means a warmer climate. But that's what we don't know is how the systems will change. So how does something like the El Niño Southern Oscillation result in specific weather systems that may or may not increase rainfall? I broadly mentioned temperature increases how much moisture the atmosphere holds by 7%, but there's a lot of variability around that. What drives that variability? What weather systems and their changes drive that variability? And we simply haven't had the tools really until now to be able to research that sort of stuff because our climate models just couldn't go down to the scales really at which weather occurred, and that's what we're trying to change. And that way, if we can better model these events, we can better understand the processes that underlie them. And that's why we're talking about weather change now, because weather is what we see, it's what we feel, it's what we enjoy, it's what we shelter from, and it's also what will drive our change to net zero. We need to harness the weather and need to be able to do that accurately and precisely so that we can actually be in a net zero world.
Great. I'm convinced.
Okay. I think we're all so familiar with climate change, but now when we're also getting questions, well, what's going to change to the weather systems? I'm interested in heat waves. Or what's going to happen? Are those high pressure systems going to be more intense or occur somewhere differently? What does that mean for people's health? What does it mean for places getting more or less windy, especially if we're going to build wind turbines there? What's going to happen to tourism if the weather systems change in particular parts of Australia? We're now at a point where we need to know more about those we're now at a point where we need to know more about those precise changes, and we now can develop the abilities for us to understand them better.
Okay, let's get cracking on that, shall we?
Yeah. Yep.
Yeah, okay.
In the next episode, we're hopping back in the time machine and going in search of the people who pioneered climate science.
Who were the first people to realise that burning lots of coal might cause problems down the line?
And how do we know about the problems? How do we use ice cores, satellite observations, and supercomputers to understand our weather and climate?
For the answers to those questions and plenty more, join us for the next episode of Totally Cooked.
And we'll tackle the climate crisis together.